I'm Toshiyuki Imamura from the RIKEN CCS. So today I'm going to talk about the contribution to quantum computing from classical numerical computing software. So today I will talk about some possible collaboration, classic and quantum computers. Then I will show the recent status of the numerical library in Fugaku, some experimental results. And finally, I will present my personal views on the numerical library on classic and quantum computer side. Okay, this slide shows the top 500 computer. I'm sorry, this is just 10 years ago. I happened to use this slide as there's a symposium just 10 years ago. So this symposium. So our K computer was ranked in the third place. But currently, it's currently so Fugaku is at the top of the list, and also has achieved a performance improvement 100 times from the K computer. So I actually remember talking about how beta-scale or exascale computing will become common in 2020. So you may have already realized that exascale exaflops systems are giving a big impact. So a typical simulation user can use 100 teraflops to 1 petaflops of resources. This is not surprising, as Fugaku can achieve this with only 1,000 nodes running out of 15,000 whole systems. We expect this to revolutionize scientific simulation. So we will be scaling up, simulating it more accurately and heading in more challenging fields. So it's my position. So importance of mathematical libraries will become more bigger and stronger in this context. Exascale computing environments require a highly sophisticated, so mathematical and computer science or vision technology. These slides show a very rough map among major simulation fields and numerical or algorithm and the corresponding open source softwares. You can see a typical algorithm are required as solving system linear equation, eigenvalue, FFT, and so random number generators. Of course, there are many specific numerical libraries. However, the very few number of them are optimized on the Fugaku. We recognize that it's a very important task to organize and maintain the system-specific numerical software package and continue maintain from old to new or future systems. This table also shows the analysis and the performance improvement results during the development of the Fugaku. Typical application was very broad, so life, climate, material, and the fundamental sciences. But the computational patterns are limited, as highlighted in the yellow column. So, as in general programming, it's possible to tune important parts of the system to make it easier to develop and maintain. In the project, we proceed with this as a part of the code design. In the same concept, so I was trying to imagine the quantum computer in my own way in this slide. So as I mentioned, I will mention later, both quantum and classical computers will use in parallel, and the quantum and the classical solution will be executed on both platforms. And emulation by a quantum simulator is also considerably integrated. In the middle of the figure, the numerical computation common to both platforms are listed as a component. Yes, here. From here on, so I will talk about the components and the libraries on numerical computation on classical computer side. So let us consider the numerical algorithm required for quantum and the classical cooperation from several perspectives. I think most of the audience here may agree that the verification of the numeric quantum algorithm on the classical computer will be essential until the practical level device is available. So in order to achieve this, there are several promising ways. Straightforward simulation of the quantum states, such as the state vector method, and also large-scale computation using a tensor operation to compress the amount of the information. The latter requires so one of the sort of renormalization technique. So, for example, DMRG and the TNRG to perform the efficient tensor construction calculation. I don't want to go into the detail of the DMRG algorithm, but so heart of the DMRG it is the calculation of the eigenvalue and the single decomposition to reduce the system's representation size. Numerical software so really excel to perform on the classical system at the moment, but so we expect to shift to the quantum system too. However, since these require not normal computational patterns, but also special ones, it's necessary to introduce a special solver that makes use of the knowledge of the applied math and the computer sciences. Another major task is to contribute to make a contribution from the numerical linear algebra and the applied math to the currently promising the quantum algorithm. For example, VQE. So here's the first speaker and the keynote speaker and the sort of other speakers are already mentioned. The VQE is considered to be a promising optimization framework, and theoretically it has the potential to outperform the classical algorithms. VQE so it's an efficient combination of the classical or global search and the quantum trial, global search and the quantum trial. And it is said to be one of the closest algorithm to practical use. However, the tolerance to error and the noise is a major issue always. So global search algorithm that were resistant to noise and error detection can use tools such as fault tolerance and AI from the classical side, and also much of the knowledge from the numerical verification and so accuracy improvements method could be used. As shown in the previous pages, the software assets of the classical computer will undoubtedly underlie the development of the research of quantum computers. So I will discuss the capability of the software on Fugaku from here. The current status of the Fugaku numerical library maintained by my collaborator is summarized in this slide. The main routines are eigenvalue, FFT, direct solver, and some others. So I don't want to mention the detail of all of them, just our eigenvalue solver, eigenexcellence. So it is highlighted here. So it provides a standard and a general type of eigenvalue program and so real complex data formats. Data layout is restricted, but it's compatible to scalar pack and other major numerical linear algebra routine. Hybrid parallelism, OpenMP plus MPI is supported. And it is, of course, available on other supercomputer other than the Fugaku. But this slide is showing the example of a large-scale simulation code developed at the RIKEN, the former name of the center. The application named the RSTFT, or Golden Bell winner, 2011. It computed 10,000 order atom of silicon nanowire and so electron density with approximately 50,000 nodes. In this application, so we need two types of eigenvalue solver. So one is CF calculation. So we diagonalize a very huge Hamiltonian matrix in there. So iteratively, so our solver is required to solve eigenvalue problems very fast. Another is for computing a band gap structure. This needs eigenvalue computation for a couple of eigenstates of a large, but it's very sparse. Two types are the very completely different. So algorithm, data structure, optimization. So yeah, so high parallel implementation, of course, different. So from viewpoint of numerical issue, so it's hard to computational scientists to implement the part of, even though that is part of them, the eigenvalue solver is quite difficult to implement by themselves. So we must share software resources. It's better to use or assemble well-optimized eigen solvers. So here I will focus on the dense eigen solver package on the Fugaku system. So not only we are developing. So the standard libraries are the eigenXR, helper, scalar pack. In addition to them, so Thread is under development as the ECP in the United States. They are commonly utilized in the parallel computer systems. And so I confirmed that these four libraries perform on the Fugaku. But honestly saying, our eigenXR is optimized for Fugaku, and it showed a good performance. So this picture summarizes the results of running the latest version 2.11 eigenXR on the Fugaku. It's a strong scale benchmarking in the left. There is a performance gap more than 3 to 10 times between the eigenXR and the scalar pack at least. And then we can see the eigenXR is performance very scalably. But the time breakdown on the right, so this shows the clear performance bottleneck in the blue markers. That should be so improved in the future. So remarkable benchmark, another benchmark. I'm sorry, page doesn't. Okay, another benchmark showed that so only 1 hour run with 4,000 nodes can diagonalize a 1 million matrix. And so we cannot say 1 million matrix calculation is not challenging anymore on the Fugaku and the exascale system. What else is needed to build a quantum emulator on Fugaku? Maybe manpower to integrate all pieces. How long do I have my presentation for? Okay. So I talked about the relationship the quantum and the classic system. So, but it might be also repeated in previous page many times. So, so from here, so I again mentioned my private or the personal review. In this slide, so due to the nature of the quantum device, it's hard to retrieve the result in the middle, the quantum calculation phase. So accelerator like a call from the classical computers are also realistic, I think. So yeah, Sato-san's R-PC remote procedure code style is very realistic. And the computational pattern that quantum computers are strong. There are very high level, abstract, and complex problems. But also they are too much challenging for classical computers. So that's why we expect the quantum system. On the other hand, there's a strong patterns for the classical computer may be so inefficient when we implement real scale or current quantum device scale. So, however, it's essential to implement the cross computation within a quantum computer as the number of qubits increase in the future. So, the current research should be very important for the future scale. As I mentioned repeatedly, quantum computer emulator is essential. So there are several implementation projects in the R-CCS to cause direct simulation quantum device. Ito-san and Yoshioka-san, they are also developing the bracket. And so Inoki-san and Soto-san, they developed the DMRG-based codes software. From viewpoint of the accuracy improvements, the improvement of the result obtained from the quantum computer is, it is just a program. So I think it can become just the initial guess or the good input parameter for the solver on the classical computer. So we can improve the accuracy of the obtained result. For example, the iterative refinement approach is a good example. And we have a lot of knowledge about low precision and the error theory on the classical computer side. So so very tight cooperation is expected. And as a standard approach, of course, we cannot stop the supporting the development of the numerical library, both side classic and the quantum computer. Okay, so I think almost time. So I'd like to conclude my talk. So the current status of numerical library and the relationship between the classic and the quantum computers are presented. So in the future, I believe that the viewpoint of the classical or computer side is still important. So in order to understand the quantum computers better, so we have to collaborate on research software asset from the classic, but also it is applicable or enhanced to the quantum computer. So thank you very much for your attention. It's very welcome. I appreciate your feedback.